Hello, my name is Jiajia Zhang, a PhD student from University of Exeter, UK. Firstly, I'd like to thank Dr. Yang Liu for his efforts to organize this symposium, providing a platform for us to share our recent research work. Now, today, I'd like to talk about our recent progress in some exciting medical device development. Let's look at the title first. Design and development experimental investigation of a Vibro-Impact self-propelled capsule robot with orientation control. So the focus today will be a capsule robot, and especially this capsule's moving angle can be tilted. The aim to design this kind of capsule is to apply to some medical applications, and this capsule aims to be used as colonoscopy. In case some of you might not be familiar with it, I'd like to give a brief introduction on what is a colonoscopy, although I believe Luigi in the starting of this session has already illustrated this part quite clearly. So colonoscopy happens when the patients need to be examined with their colon disease, and a lung tube will be inserted from their rectum by a doctor. The supporting force to be inserted from their rectum forward usually takes place at the sharp angles of the colon. Accordingly, the reaction force will be applied against the colon wall and cause great deformation and great pain. In this case, potential dangers exist where the patient might suffer from sedation and expose their colon to perforation. So to give a solution, we designed a 4-coil soft-tethered capsule colonoscopy driven by onboard magnetic field in a surprisingly small scale, which is 34 millimeter in length and 15 millimeter in diameter. We have chosen this size after evaluating the real colonoscopy used in the hospital and tested the length to be capable to travel through the sharp angles of the colon. The capsule's outer surface is completely smooth, and it can not only move forward or backward, but also with adjustable angle. So how did we realize all of this? To start with, the capsule is driven by an onboard changing magnetic field, and is generated by the electronic coils. A permanent magnet inside the capsule can be vibrated and generate constant impact on the capsule's body. This kind of force will propel the capsule to move either forward or backward, depending on different control parameters, namely amplitude, frequency, and duty cycle. As for control methods, we have built up two schemes, namely 1-coil driven and 4-coil driven methods. Due to the time limitation, I won't go into too much details with both methods, but I do want to go inside 4-coil driving methods a little bit. As you can see from this slide on the left-hand side, A and B describes the working scenario of 1-coil method, and C and D describes the 4-coil methods. The picture on the left corner may help you to more straightforward understanding. The blue cylinder here represents a permanent magnet and is placed inside a ball bearing so that it can rotate in 3D space freely. When we turn on one pair of the coils, A1 and A2, on and off constantly, the magnet is able to vibrate inside the space and make impact on the frontal and the back constraints. But as the magnet is able to rotate itself almost frictionlessly in the space due to the existence of the ball bearing, we need to turn on the coils B1 and B2, serving as auxiliary coils to provide additional torque and lock the magnet to this angle. So in this case, the capsule can move either backward left or forward right by changing the vibration frequency and the duty cycle. When we flip over all the setups, like putting B1 and B2 as vibration coils and A1 and A2 as auxiliary coils, we can get the capsule moving into other two directions. So by changing the control parameters, we can get the capsule moving towards any directions in a two-dimensional space. We have also done some analytical and simulations on calculating the force generated from the coil to the magnet to monitor the magnitude of the force and to make sure the magnitude is sufficient enough and will do no harm to the human tissue. Let's have a quick look at our experimental setup. There are 4 identical coils inside the capsule and they are individually connected to a motor driver module. The winding direction, circuit connection of the coil, and duty cycle signal have been carefully combined together to decide the generated magnetic force direction, and the coils are provided with certain amplitude, frequency, and duty cycle current signal. A video camera is placed on the top, and with a timer and a ruler, the average speed can be measured. We conducted 1 and 4 coil driving methods, and the experimental results on the average speed are shown separately. The experiments are repeated 5 times to demonstrate its robustness. We have found that at certain control parameters, the capsule is able to move steadily backward. We have also summarized the maximum average speed under different control parameters when the capsule is freely moving on the 2D plane. And we found that under certain parameters, the capsule is able to travel with 13 millimeters per second. Then we adopted this case of control parameters illustrated here. So 4 coil driving method, frequency of 30 Hertz and duty cycle of 60 to conduct 2 more experimental scenarios to demonstrate the capsule's capability moving inside different environments. The first one has been shown in the previous slide and moving on surface where the orientation movement can be observed clearly with the speed explained here. And the second one is inside a curved tube, traveling with a relatively fast speed, even faster than on a smooth plane. And the last one is on a real porcine intestine tissue surface, and the capsule demonstrated itself moving successfully, but with a relatively low speed. You may be concerned about potential damage caused by this device and the heat dissipation issue, but we can assure you that it won't happen because our prototype only generates around 60 millinewton impact force according to our measurement. And we also monitored the capsule's temperature and it stays stable at 25 degrees after a long time performing. So finally, I'd like to take you to the journey we have passed through designing a Vibro-Impact capsule system. From the standard size capsule, we made it either large or small, with coils either implemented inside the capsule or outside, or a capsule with a soft shell, or even some crazy ideas like magnetic soft shell. So I hope the designs can provoke a bit of inspirations and hope to make some advances in the smart medical robot area. Thank you for all your attention today, and I'm happy to take any questions.